Okay, I guess we can keep going so we're not here till 2 in the morning. We're still recording apparently. We'll start by getting into some of my ideas and ways of dealing with data and management and some of the tools that have developed. And there is a good chance that through University of Florida here that some of these tools may be more broadly distributed or whatever. I'm trying to pay it forward, as they say, and my viewpoint these days, unless the next generation continues with bad acoustics and everything, and I can impart as much as I can on what I've learned with 20 years of recording, you know, I've wasted my time. There's no point in me wandering off and covering myself with leaves in the tropical forest somewhere and moldering away and then having nothing carry on. So having bat conservation carry on and the next generation moving forward and new innovations, you know, so I'm happy to help anybody I can within the limits of my time and parameters. So, data by the numbers. I don't know how many are familiar with the comic strip PhD comics. So, there you go. And we'll talk about the amount of time it takes to collect data, process. Critical to avoid big data paralysis. Analysis paralysis is a state of overanalyzing, overthinking a situation so that a decision or action is never taken. Essentially, it paralyzes any outcome. Important to realize you don't need 100% perfect ID on all your call files. Get over the fear of making a decision which could lead to an erroneous result when looking for an absolute answer. With any ecological data, we're never, ever going to know what absolute values are. Decisions on presence, absence, relative abundance, wherever we're working, doesn't matter what critter you're working on, it's always going to be an estimate. You're always going to have a probability of making a type 1 or type 2 error. In the case of a null hypothesis, that a sequence is correctly identified, you know, you reject a correct ID, type 1 error, or fail to reject an incorrect ID and assume it's correct, type 2 error. It happens. Just be aware that don't paralyze yourself, don't stop and tear your hair out to make a decision. The sheer volume of acoustic data can be daunting and nearly paralyzing. If you don't manage it well from the beginning, you may need to be avoiding sucked into the data vortex and nothing happens over and over and over. How much will you record? How much storage space? Depends on how you're recording. If you're recording full spectrum wave files, think gigabytes or terabytes of data storage. 20 files, in this example, 36.6 megs, 3 hours of recording, you know, 3,500 megs of wave data, and you can see the individual file links on the right. If you're recording in zero crossing format, think megabytes, 29 files, 199K. 1 year of nightly recording, dusk to dawn. And I did 3 years of nightly recording from sunset to sunup, comparing with weather, rainfall, wind. Still hadn't been published yet. I have to sit down and work all that out. But a year's worth of data is zero crossing files with less than 700 megabytes. Fits on one CD. So storage is one data management issue that you have to consider, how you're recording. How many files? Well, in zero crossing, the files are smaller in size by an order of magnitude or more than WAV files for full spectrum. Generally, 15 seconds or less in call length. WAV formats, you're going to have fewer files, but much, much larger file sizes. Also, much longer duration. Passive monitoring in an active area can easily result in 500 files per night per station if you're recording in zero crossing. So how much data is in all of that? It's more than just the number of files. It's not unusual to have more than one species in a recording, as we've already seen. In active areas, you can have 1 to 3 species in a single file. In the New World tropics, I frequently have 4 or 5 species in each individual file. You may also have, and almost regularly will, low-frequency files from wind noise and insect noise. You can have hundreds and hundreds of files that are just noise. Many are overwhelmed by the data. As I said, the passive wind monitoring areas, they were only analyzing subsets the first 15 minutes. So don't throw out 3/4 of your data. The other question is backup or not to back up. On-site backup is real easy, and current really low-cost terabyte hard drives are a great investment. They're really inexpensive. Disadvantage is if a major disaster, your boat turns over on a river or your campfire spreads and your tent burns down or whatever, you still could lose all the data, but probably not. Cloud backup. It has the advantage of off-site storage. It's deceptively simple, but extremely costly. The time involved for a backup online could take you days, and then if you have to download any of it again to go through it again, days again, depending on your Wi-Fi connection. If you've got a mobile hotspot or you're trying to use a cell phone or whatever, boy, the tech companies are going to love you because you're going to exceed your data allocation in probably the first 20 minutes or so because it's huge files. So cloud backup is not really the way to go, I don't think. You should invest in a handful of small external storage, and then if you have an office, take one home with you at night. If you're only recording stuff at home, give one to a relative to keep as a backup, just in case there's some disaster to your house. General rule of thumb, you only need to back up your data as often as if you wish to avoid re-entering, analyzing, or collecting it. Or if you're working in the remote areas in the tropics, only when it can't be replaced at any cost. You're not going to go back down to Suriname because your grant was only good for 3 weeks and you didn't back up your data. You're up the creek, as they say. You can't replace it for any cost. Even if you go back a year later, are the conditions the same? Ecologically, probably not. Always, always, without fail, keep your original data untouched until you've finished all your analytics. Everything's been done. Only edit a copy of your data. Keep your original data in a hard drive somewhere, off your main computer or an external storage drive, whatever, but don't touch it until you're finished, because you never know where there's going to be an oops, I was just moving this whole set of subdirectories to the other tree and oh, that really wasn't supposed to be delete. Oh, that drive doesn't really have a undelete function on it because that was only my C drive, and this is my G drive, and oh, it's gone. You know, keep your original data. Anything can happen. Software can glitch and corrupt your data, and then you're going to have problems. Data management and analysis embrace the concept of tidy data. Raw data in the real world is often very untidy and poorly formatted. This doesn't apply just to bat data. This applies to anything you're going to be doing. Causes of messiness, and you see this all the time. Column headers are values, not variable names. Multiple variables are stored in one column. Variables are stored in both rows and columns. Multiple data types are stored in the same tables. One type of data may be stored in multiple tables. This can really be a problem, and it costs you an enormous amount of time. So you need to get organized at the beginning. Doesn't matter what you're doing, whether you're counting, fruit flies, or whether you're doing bat calls or looking at botanical specimens or whatever. If your data isn't in the correct format and managed correctly, you're going to be really spending a lot of time spinning your wheels. What is tidy data? Said to be tidy if it satisfies the following conditions. All the observations are rows, all the variables are in columns, and each unique data set is unique and by itself. This makes it easy to carry out any data analytical work you want to do. Hadley Wickham, who is also the author of the ggplot, the graphics and graphics R program, has a whole series of things, and those of you that use R, I say things, programs, there's a lot of R packages that help you tidy your data and everything. But this is really important. It's all often said that 80% of your analysis is spent on cleaning and preparing the data, and it's not just the first step, but it has to be repeated over and over until you've got everything sorted out. Well, for bat calls, 80 to 90% of your time is going to spend working on analyzing the data, adding identifications, IDs, or other information to the bat calls, such as harmonics, such as feeding buzz, such as clutter calls, such as social calls, so you can actually use the data in a meaningful way. How I arrived at a data management protocol in analysis. Dealing with large data sets from the get-go. Generally, I would run 10 passive monitoring stations when I went into an area for 10 to 14 nights. Each station, 500 files a night, each file more than 3 species. Estimated for one survey session, I could have 150 to 210,000 data records, just a couple of weeks of work. Working on conservation issues in developing countries, it wasn't uncommon to have to complete a requested protected area service either by a government agency or an NGO, and then they naively say, well, you can give us the answers by next week. It's like, it's like, well, turns out, well, we didn't have TV in the jungle, so, we spent a lot of time analyzing data. But generally, we were able to do that. But managing the data, it was one thing, and I got pretty good at that. Doing the analysis turned out to be repetitive, and we'll talk about that a little bit. Recording from Mexico to Bolivia and Cuba. I was fortunate to go there for 5 weeks in 2006 and record with some Cuban bat biologists. I realized that generating the key data that you need for your ecological stuff to compare relative abundance, presence, absence, mapping species densities, which are used to evaluate habitat use and all of this, I needed to also refer to previous surveys to provide comparisons between either locations in Central or South America or between dates. And the analytical part was very repetitive. So rather than trying to reinvent the wheel every time I did a project, I started working on a system to automate a lot of this. I started with a simple access relational database. And you need to have your data, I would say, no matter what you're working on, in a relational database, because you can manage it and query it and everything very quickly, and it makes data management much, much more efficient. This quickly evolved into what I call the ADMS, the Acoustic Data Management System. More and more complex programming became embedded in the program to automate and streamline all these repetitive tasks. As an aside, spreadsheets like Excel are not databases. They weren't designed to be, and you should never use them as a database. How many times I've seen colleagues in other countries and students, oh, I've got a database, it's all here in Excel. One screwed up sort where you didn't have everything in there, your data is scrambled like shuffling a pack of cards, and there's no way of getting it back and associating records with dates, times, species, whatever, unless you've backed up your original data and never touched it. But I would always have people, what do I do? My computer crashed, the hard drive crashed. Hard drives, it's not a question of this, it's always when. Your hard drives are going to crash or your machine's going to croak. You better have it back, your stuff backed up somewhere else. But don't rely on spreadsheets for total data management. They're very useful for some things, and I do use them for a lot of things. In the early 2000s, I began to explore rapidly growing R-based tools for analyzing a lot of data. The ADMS has programming code that's continually evolved and updated to provide additional functions and utility to essentially spit out tidy data that I can just suck right into an R program or module, and there's all kinds of neat ecological packages in R for your analytical stuff that you can do. A review of relation database tables and program functions will be presented, but the workflow begins with your raw data, the BAT calls that you've recorded. 80% to 90% of your time revolves around dealing with your raw data, recording the data, backing it up, converting it from wave to zero crossing if necessary, then adding the metadata. Metadata is critical. Processing the acoustic file data, you have to add species IDs. Depending on your research questions or what you're doing, add other information such as feeding buzzes, social calls, gives you more insight on how the bats are using the habitat and environments. Back up your edited data. Also, you're going to archive the call data as you're complete with your analysis. And then the header data is imported into the data management system. Why did I choose analog? Aside from the measurement issues discussed with slope and some of the other things, it's optimized for very efficient data management and processing. Oh, also to mention, it's free. All the updates are free. Chris is constantly updating it, and it's evolving almost on a monthly basis. There are new updates. You can go to a beta website he has and download the new updates with all the new features that are added. Preparing your data. Well, you use Analog, and it's designed for Anabat or any other zero crossing file formats that are out there. The most recent release version of Analog is 4.3F, and who knows, it could be H or K by today. This was like 3 weeks ago. It's optimized for species identification. You create your own user-based species filters to help you screen and scan. And we had a question here about low frequency or flat low bandwidth calls, narrow bandwidth calls that may overlap with other species just visually on the screen. You can create filters to actually scan all your data at one time, and it'll actually extract them. And back here we were during the break talking about some data from the National Park Service. Very quickly, all of the data could be scanned at one time and separate them into different components, which will show you how to do that. You can use your own filters or use existing filters for known species. And that'll help you vet the calls that the auto ID thought that they knew what they were doing. Easy to see multiple species and files. You look at complete call sequences. So many of the full spectrum programs, Sonobat, Bat Sound out of Europe, Kaleidoscope, depending on what you're doing, you're looking at single pulses at a time or little short sections of pulses. And I'll show you how this all works with a demo when we're done. Batch handling of data for adding the metadata is optimized very quickly. And you can extract call parameters if you need to. The important thing is if you're recording with Anabat or Wildlife Acoustics song meters, you automatically can have zero crossing files. No conversion is necessary. If you're recording using full spectrum modes, the output is WAV files, and those need to be converted to ZC. Kaleidoscope has a free version, their viewer, which also has the conversion routine in it. So you don't have to spend $1,000 every year for a new license or $390 or whatever it is. You can get the free version and it'll convert all the files for you. And it works really well. It may be necessary to rename your zero crossing files to match the analog format. Pedersen full spectrum recorders from Europe and some other file formats may be problematical by the way they name the files. The Anabat file format is based on legacy, the old DOS-based file format where you had 8 letters, numbers, or whatever, plus a dot and then three letter or digit extension. Anabat files, the last part of the extension is that £, and that automatically identifies all the bat call files, so Analook will read them. It's not case sensitive, so in this example, the RC19 there is exactly the same as the lowercase. It reads them both the same. So they're not case sensitive, but the file name is important. The file name is actually the date and time of recording. Analook decodes this. I just processed a whole bunch of new Cuban data that was recorded in December from a Canadian biologist that sent me all the data. She didn't have experience doing the IDs, and I offer to, for a lot of the New World researchers, I'll just ID the calls for them without, any big deal, because they get contributed to the master database. But this particular call up there, that RC191801.11, actually translates to December 19th, 2017, and then 18 hours 01, so a minute after 6 in the evening, and 11 seconds. So the first digit is actually the year. It's a modified hexadecimal, so R is 2017, C is the month. For all the first 9 months, it's simply 1, 2, 3 through 9. When you get to 10, 11, 12th month, there's only one digit available, so that becomes ABC. And then you have the 2 digits for the day of the month, the 19th, and then you have the hour, 1801, followed by the seconds. So the names are important, and you can actually see how that is. It's not really critical that you know how to decode them, because this is all done automatically, but it is important that the file names are fairly correct in order to use the whole system. The foundation of the data management system and automated analysis is the header text file, which is exported in analog. After you've added all the identifications as far as you can go and all the other relevant information, then this is exported and imported into the data management system. This is not a 4 to 5 or 6 day workshop on how to learn intricacies on how to use all the features of Analog or how to ID all your BAT calls, but it does show an iterative procedure that's been developed so you don't keep reprocessing the same data over and over again. As we talked about before, each ANABAT file is a recording event from 1 to 15 seconds that has the BAT call in it. But included and embedded into the call file, each individual file, is header data along with other information you may have. The header data includes metadata related to each individual call file, such as who did the recording, what equipment, where, when it was recorded. This is all entered and edited in Analog, which I'll demonstrate shortly. Metadata is critical, and it's the very first thing you do with any data you have. You don't worry about species, IDs, you don't worry about anything else. First thing you do is add your metadata to all your call files. Without your metadata, they're useless. It doesn't matter if the IDs are 100% correct. It's just like taking a specimen of something that could be extremely rare, putting it in the museum here. If nobody knows when it was collected, where it was collected, or whatever, it's of absolutely no scientific value. Absolutely none. Same thing with acoustic records. Every one of your acoustic files that you're recording, even if you can't identify the species at this point, are the same as museum voucher specimens. Each recording file is a valuable data element that sometime in the future we may be able to identify that species, and once that's done, all the similar calls like that will update all the distributions wherever it was found, you know, from Mexico to Bolivia or whatever. But without the metadata, your data is absolutely useless. So I'll segue to do a short Analog demo and see how it show you how it functions, and then continue in the last section of the presentation with showing some of the analysis, the outputs, and how the acoustic data management works. This is what I'm using for the data is a subset of a passive monitoring station that I had in Belize. I only took 3 nights. This was like 9 nights of data or whatever. And to demonstrate the workflow, these have been renamed as if they were 3 separate locations, but the procedure is exactly the same. Again, 80% of your time is going to be dealing with your call files, adding metadata, which goes really quick with the editing tools in Analog. Taking a quick look at the data for an overview, which is related to some of the R programming and ggplot functions. Use of filters when you get ready to scan your data. Filters help distinguish what you want to look at or identify the BAT calls, and I'll show you how the filters work. Use of scanning. You can scan your entire data set. Like in the case where I was doing the climate-related BAT activity, I could set it as a root directory and scan 3 years of data from multiple locations, and then it would identify everything for me that passed the filters that I built. no matter where it was on the hard drives, different directories, different drives, could be on drive A, drive C, and it will scan all of it and give you a report of what the species are. Once you've done completed all your adding all the information you need to do on the individual IDs, you move the data to an ID added directory so you don't have to repeat going through the same data files over and over and over again. You have 10,000 files that you recorded in 3 nights. Maybe the first pass you've identified 5 common species. Strip all those out and they may have been 90% of your bat calls. You only have 10% of your data left to work through. So it's a real efficient way of doing it. Anyway, we'll go through a couple of examples on that. Again, we as people are great at pattern recognition. Sorting the calls that have patterns and parameters that match marching. Oh God, I thought well, spell check said it was correct. Matching known species. If my wife had seen this, she'd have shot me. She could look across the room in her office in Belize and go, oh, 3rd line, you've misspelled, and she'll keep on working. And it's like, oh, I didn't see it. Anyway, scanning and grouping your files makes it much easier to use. Also, we're putting out fact sheets in Lucid ID keys. The fact sheets include the call parameters, like I've showed you once before, with the statistics on the frequency bins of how often they're encountered, and those will help people identify the species. And with that, I will stop, shut this down, get a drink of water, and then we'll do the next one. Oh, actually, no. Stop. This is a little slower with the... Okay, what I'm going to do here, I'll actually sit down. It's easier to use the mouse. I'm opening Analog. And what you have are the call data displayed on the screen. And this is the frequency range that's displayed. This is user defined for most neotropical things. Going from 10 to 110 kilohertz is adequate. For some areas, I would even expand it up to 120, 140 kilohertz for some of the high frequency bats. Or if I was working in an area only looking for low frequency things, I would change the display. This area up here changes the display. Right now we're at 10 millisecond ticks all the way across for the frequency display. We can go down to real time, and so that's less than a second. That first tick mark, you have a 0, the first tick mark is 1 second, next tick mark is 2 seconds. So you don't see much in the way of call shape. You know, you can slowly expand the frequency, but generally F7 is what's used. Sorry, the mouse is with this projector here, it's a little slow. It's standardized at 10 milliseconds across. This area here are all the species codes, and the species codes in the master database are actually 3+3 species codes. In North America, a lot of people are using 2+2, which is the first 2 letters of the genus, first 2 letters of the species. That doesn't work for all the New World species because there's too many overlaps. So I use first 3 letters of the genus, first 3 letters of the species, and that works for all of them. But these can be added without any trouble. And what happens is when you click on these, down here on the bottom, you actually see the header data, and it just adds the species in there Every time you click on it, it adds another species. Well, we don't want to do that. So I'll undo, and the header data itself is this whole section down here. This is where you enter a location name that's unique and then add notes such as, oh, it was raining, deluge, or recorded, next to the barn or by a pond, whatever notes you think are useful, you can add there. You're limited in size for the location by this field right here. But this field continues on across. You can actually, it's much wider than that. It just doesn't display that much. But you can edit all this. Now, you're not editing one file at a time. That would be very tedious. What we do is there's a utility called marking, and you simply mark all, and this marks all of the files. You can tell all the files in that directory are marked, and actually at the top shows us where the data is. Sorry, the mouse is a little slow with this projector here. But right up here at the very top, you can see the actual directory, C drive, bat data working, examples, monitoring, and then it has the file name there. And then the plus sign after it just means it's marked. But what we need to do, boy, this, I don't know if it's a question of the mouse not reading on this. Let's try the, seems to be a time lag with the projector. You can go to under Edit, Global Header Change, and now you can go in there and say I didn't want to call it Dummy Site 1. And just say OK, and it warns you it's going to modify all your data files, are you sure? And then it goes through, you see it processing. This little laptop is almost like a tablet. It's very slow. So normally on my workstation at home or anybody's real computer, that would go really quickly. But now all the files have been renamed in that directory. And actually, and just to show you this again, there's 3 different directories here, each with data, and then there's a folder that's created that has nothing in it at the moment called ID added. Right now, I've just added everything that was in, or edited everything that was in that particular folder. I'll just minimize this. So it's gone through all of those files, and once you've added your data, and this spec field is used for the system for who's recorded the data. If you're contributing the data to the master database, then you would receive your own ID code or whatever. It could be an acronym for your name or whatever, and then that's added to the actual master database, and that's all related to all the calls that come out. But one of the features, once you've edited your header data, also it adds your GPS location data, and that's added through another utility. But what to look at now is using one of the keys on the keyboard, which is the right bracket. You can just start scrolling through the entire data set. This is looking at the call files for everything in that folder. So real quickly, you can go, oh, okay, well, I see some naked back bats up at the top. There's some mollusids. Okay, A lot of naked back bats. Okay, what else is in there? Oh, there's some Lazarus. Oops, we just saw, let's back up slowly one at a time. I just saw a low flat call pulse. What was that? Oops, overshot it. There it is there. Oh, okay. Now I know what that is. That's Diclodurus, the big sac-wing bat that flies high overhead. But this gives you a way, visually, you can really quickly go through all your data. And I'm noticing that the screen, as it's projecting, is much slower than on my computer here. But this gives you a way to actually look at all your call data really quickly and then get a feel for what you've got in your data set. So now you know pretty well when you start. I'm going back to the beginning. What species complements you might have, what families, what genera. So now you can start worrying about thinking on how to add IDs. And in this case, I've added a whole lot of IDs. This is Diclodurus alba, the low frequency embalanurid. This is Psychopteryx bilineata, the typical two-note embalanurid that flies in the forest. So a lot of these already have IDs added. I want to demonstrate how to use filters now. I didn't want to sit here all day and identify everything. There's a section called filters, and this is where you load filters for species that we already know, and most of them I've given names that match the 3+3 naming convention. And what I'm going to do is load a filter for the common mustache bat, Pteronotus parnellii. And all of a sudden, the screen changes color. Why is that? Well, none of those call pulses match the mustache bat. One thing you need to make sure is that you have the off dots that turned on, and if you don't, you won't see anything on your screen. The calls are there, but using off dots, this shows you all the calls that are in the particular file. And down in the lower right-hand corner, I'm going to not try and move with my mouse because it's too sluggish. You'll see on the very bottom, it shows what filter is actually being, or is loaded, the PTEPAR, the Pteronotus parnellii. And the extension ABF is simply Anabat filter. Well, what does that mean? How does that help me? Just scroll through until I find one? No. What we do is we go up to File, Marking. Sorry. Mouse is sluggish. Mark if it passes filter. It's just going through all the files in that directory. It found 88 files that match that filter. Okay, and now they're marked.
Can you say anything about how this, what does the filter mean in this case?
The filter, well, I'll actually show you a sample of it. What it does is screens out all the species that you're not interested in. So you can identify things.
Is that based on frequency band similarity, or is it something else?
Yeah, it's all the call parameters that we looked at earlier in the session with the durations, slopes, characteristic frequency.
Okay.
So what I've done now is done a global header change. All 88 files that were marked, I've just added in the species field Pteronotus parnellii, the code. You sure you want to mark all your files? It warns you, so you don't do anything. Okay, they're marked, so now what? Well, you go up to another little tool under filter and use disperse. What this does is this will scan all the files in that directory that have something in the species header area, whether in this case this is just marked as a fragment. This was not an identifiable call. That's an example. You can do a lot of things with the disperse. In this case, I'm going to create a list file, run, and it's going through 2,000 some files. It went through all of those. It's going through a second time, and it just went through 2167 files. You go back up to file, and then you load your list file. Ooh, I forgot where I was. And you have a file called sorted with a extension ANL, which stands for Anabat list file. We want to open that. And what you get is this neat little window. It says choose a field. This shows every file in the whole directory that has a species name added to it. Well, all I want to look at right now is the mustache bat file. So if I do that, now all the calls in that whole directory, the 2,000 some files that have mustache bats in them, are displayed. Now we have the off dots on, and you can see there's some fragmented calls here that are also mustache bat calls, but it doesn't matter. You've got a number of calls there. You've identified it for that species. The other species that was there is the naked back bat, which is in the same family, the Mormolopidae, but that's already been identified. So now we can scroll through and just make sure the filter, I say the filter didn't screw up, or you didn't when you created the filter, and you put in the correct parameters so you don't have any fragments of some other species in there as well. And you can have some overlap if you're not careful. So just hold it down, look at all the files, and lo and behold, every file that had that species in it is now marked. Okay, what do we want to do? We need to get rid of those because we already know what they are. Unmark all. And now I did unmark all just to be safe, because now we'll mark those. This only marked the 88 files that had the information on these species. Now, move if marked. We're actually going to move those files completely out. This is your whole data tree. And we're going to store them in ID added. We're going to move them there. Okay, they're gone. And it warns you again. It's going to delete them from your hard drive, but only where they were. It's already moved them to the other location. Yep. Okay. Want to make sure that so you close that window, and now all of those files that had the correct identification for the mustache bat are in a separate directory. They're no longer in the data that you're processing right now. So let me navigate over.
So like this, you're extracting like each species every time.
Yeah, it's an iterative process, and once you've added all the species that you can identify from your screen, or before I go on, let me there's another information folder up here that's useful if you're working in an area that a lot of species aren't known yet. You can just call something an 18 kilohertz vespertilianid, a 16 kilohertz molossid, or whatever. These are sono species, just like a morpho species that you bring into a museum. We know it's different species, we just don't know what the taxonomic name is. And this is still useful because you've identified it, maybe not with a valid taxonomic name, but you've identified your data. And this will then still allow you to analyze your data for ecological attributes, species composition, how much diversity is there. You just don't know what the actual species name is. So, all right, let me go back up to where I was. And we'll go to the ID folder just to look at the mustache bats. And this just opened them up. So if we go to the filter section, again, this is not a complete course to teach you everything there is to know about doing this. This is about data management. So we've opened the filter. We're going to edit the filter, and here's the filter. Oops, missed a step. This is real easy. You do this stuff all the time. Hitting the M key actually displays all the call parameters on the screen so you can see what you've got. The body of the calls in this case are the bright red parts, and then it's measuring slopes of these other things. But let me go back to edit the filter. So right now, the filter has many sections. The first section is the calls. There's a whole text document that I can provide to Farah that she can distribute to people, or you can email me and I can give it to you on how to use filters. The Analog has a complete manual on how to do filters. Smoothness has to do with, none of these little fragmented pieces here. This is all extraneous noise, not part of the bat calls. Go to the next tab. This is the body of the bat call. Right now, what I've ticked, this is the characteristic frequency. I'm measuring or accepting for the filter between 58 and 65 kilohertz. If I turn that off and turn off the frequency of the knee, that doesn't change a whole lot. That's still showing that species there. Let me go to the frequency tab though, and if I turn off these frequencies and turn off the time, these are very long duration calls, all of a sudden other calls frequencies and everything will pass through the filter. Right now the filter is not very tight. It's accepting calls from this range here, although the mustache bat has a narrower call range. So if we go back to the mean call range of using this, it's filtering out some of these, but there's still some fragments down here that it's accepting. The maximum frequency range, we want that. You can exclude parts of the call. So if I wanted to exclude, let's say, calls from 65 to 300 kilohertz, that effectively cuts out a lot of these pulses, but there's still a lot of other pulses for this other species. The initial slope isn't important. Body of the call, characteristic slope is useful. If we add the characteristic slope, which this bat has a constant frequency call, the characteristic slope ranges only from a -5 to a +5. Automatically, that killed any of these fragments or call parameters up here. for this other species. Even though they're in the same file, it's only identified these. You add the time. Right now the time is turned off completely. All these parameters are going to be available to you from the fact sheets are going to be available. If you wanted to use the percentage of maximum, the PMC, you can use that as well, and there's parameters for that. Also, you define how many call pulses you want your filter to identify before it recognizes a bat. Well, you don't want just one fragment that might match, so maybe you have 2 to 10 or 2 calls for every 10 seconds. Or maybe you need to say, okay, I want at least 5 pulses within a 10-second frequency range. Well, that turned that off completely. So there's actually more, or the fewer calls in there. So if we go back to 2 call pulses in 10 seconds, it'll pass the filter, and then you also add the time between the calls. So the filters are customizable, and when you're done, you save them. If you get a new filter, you come up with one that's completely blank. You have a complete blank slate, and it recognizes everything. So the filters are extremely useful to very rapidly go through your data. And this isn't auto ID. You're going through and rapidly scanning through, and you can manually vet your calls that pass the filter in a couple of minutes, depending on how much data you have. This isn't auto ID, it's relying on you with visual recognition and looking at parameters. So you're going to be real good at this if you spend time on it. And it's like any acquired skill. You know, the upfront time, you know, honestly, with current neuroscience and learning, intensive practice and skills, whether you're trying to learn oil painting or whether you're trying to learn to play a saxophone or whatever, you don't work on it 8 hours a day because your brain does freeze up and your learning diminishes. That's why cramming for finals never works if you didn't learn it to begin with, because your brain doesn't handle it that way. But if you do it in intensive 1 to 2 hour sessions and break it up, maybe a couple sessions a day or once a day or twice a day, and then keep scanning through your data, you'll learn how to do it fairly rapidly. So looking at the call data and everything, this is how all of this works for processing. You've done an iterative run through the data. As you've processed the data, added the call data information in the species section, you get it out of there. And now when we go back and look at the other species, and I'll close that filter, and it remembers where I was. We're still back in the original folder there. And I'm going to run a new disperse because we no longer have the mustache bat in there. We've removed those files. And we'll just take a quick look at one of the other species. And you do this iteratively. Every time you've finished processing a file, you load a filter and scan it. The other thing you can do is you actually use a scan file. And the scan file allows you to define your directory tree. And since I hadn't opened this one, we're going to go all the way back down. And in this case, if I just put it there, this will scan all 3 directories. And it doesn't matter how many you have. You could have 249 subdirectories out there, but this will scan all of your data. And then you need to actually have a scan file loaded. And let me see. This is a Mormolopid scan file. Let me open it for you. In the scan file, you actually define what filters you're going to use. So here you stack all your filters. In this case, these are filters for every species within that family of bats. But this is a Cuban species, and that wouldn't be in there. I'll get rid of that. We'll get rid of that filter, this filter, and this filter. And now we've edited that. Okay, now you need to define where you want your data to go so you can look at it. We don't want it to go back under filters. Let's go to our examples, and we'll just put it under examples. All right, couple things we can do here. We can create an analyst file, which is what we're going to do, or if you do an ANA measures file, this will extract all the call parameters from all the calls from all the species that are in there. And I'll show you why you may want to do that when we get into the output. But right now we're creating another list file, which is just like the disperse. Only this time we're scanning multiple directories, multiple folders. And it's going to go through and scan everything using all 5 of those filters. And it'll jump from subdirectory to subdirectory. But this could be your year's worth of data, your whole field session. It's scanning it all at one time, grouping your data for you based on the filters that are already for known species.
And you can add as many filters as you like.
Exactly, yeah. I have them grouped by family, so when you're actually reviewing the data, it's like for the US, you have molosids and vespertilionids. Unless you're working in the Southwest, then you'll get some of the mormolopids as well. Okay, so that's completed. And just like we did with the disperse, which creates a filter, you go up to the file format, go to open an analyst, and we called it sample, so we know what it is, and looking at the date time, that's correct. And what this gives us, choose a field. Okay, well, let's look at the Mormolops megaphylla. What this is now doing, apparently that filter wasn't set very well, because that's not a Mormolops. Let's see what we've got going. Oh, this little machine is locked up at the moment. I see what's happening. Trouble with having a laptop that's really no more than a tablet. The processing power that you have on your phones is probably better than what I have on this. You need to load one file at least on the screen for Analog to be working. And in order to see the it's like I don't know if it's the internet connection is unstable, it's telling me. I guess this is part of the projection or whatever. You go up to none, and this unloads the filters, and then you can see all the call files again. Okay, let's look at the naked back bats. Okay, now we're looking at the naked back bats. I don't have a filter loaded. And if you see down in the bottom right here, filter none, you know, before we had the mustache bats. But you can now manually go through. And what you're looking at are the files, no matter where they are in your hard drive. These files are dispersed in 4 or 5 subdirectories. It doesn't matter. Now you can manually go through and vet that your filter was working, or you may need to tweak it and refine it. A lot of times I set filters fairly loose, so they include a lot of other extraneous call parameters, and then go through a second time a little bit tighter. But it doesn't matter where you are. This will continue looking at all the files through all the different subdirectories. And then once you're done with this, we can go again, mark them all, move them out of the data files into the ID added, and then they're gone. You've already processed them. They're somewhere else. So as you go through the next iteration, maybe you have half as much data to look at. So it's a very quick way to go through and process your data iteratively. The scanning is really good with that because it'll scan and identify files for you based on your filters, no matter where they are in your hard drive, depending on where your initial root directory is set. So that's a quick introduction to why I use Analog. It's just really quick way to manage your data. Immediately, you can manually edit all your header data in a batch mode. It will mark and identify thousands of files at one time. A lot of these dusk to dawn nightly data sets in one location, hundreds of thousands of files. It'll update the header data in 15, 20 minutes, if that long, depending on your processing speed on your machine. If I'm home on my big Dell workstation, you know, it's, you know, a minute or so if you had hundreds of thousands of files. On this thing, you know, a lot. So that goes through why I've chosen that. Again, you can always look at the frequencies by hitting the M key, which is short for measure. All of these instructions how to use Analog are available, and we can get that to people. Again, that's not the purpose of the call. It's more about how to manage massive amounts of data efficiently and quickly. And using the iterative process of scanning different filters, you can quickly eliminate all the species you already know what they are. If you've made a mistake in your filter, I identified this is the wrong species. You can clear it, add another information. Oh, that's a clutter call. Oh, well, it is a clutter call, but it also is the naked back bat, so I can click that. You can also just manually put your cursor down there and it turns white, and you can manually type in there, but that's really prone to typos, and it's tedious, and it takes a long time. You know, why not just use the tools that are there, and you can quickly add them. So that's what we use Analog for. Oh, wonderful. Time for thyroid meds, so I don't go to sleep. Yeah, again, thanks to Agent Orange in Vietnam, all sorts of autoimmune issues. Oh, I needed to show you one other thing here, and now, I don't even see my desktop thing. Oh, here it is over here. Moved. Let me go back into Anabat one moment. As I said, the bulk of the work, you're going to spend 80–90% of your time doing this, adding species, moving the files out. Depending on how much data you have, this could be done in a couple of days, a couple of weeks, maybe a couple of months. Under the Tools section, you go to Ahead. This brings up a whole menu of options, and this allows you to fix division ratios for the zero crossing if it's incorrect, how to add positions to your header data, the coordinates. It can, if the times are incorrect on your file names, you can correct all of that. But importantly, you download the header data. In this case, I will run a download on that one, and then let me go down to ID, added, and let me download this. Okay, that was really quick. All right. What the header data does is comes out as a text file, and this is what's imported into the Acoustic Data Management System, which we'll demonstrate in a minute. You can open it in Excel or Notepad Plus or something like that, which before you do any analytical work in R, you'll need to actually open it and delete the #, which I'll talk about. But what this is, it shows you the file name, where the original data was, and this is all just has to do with the data file type. It shows how the division ratio was on the zero crossing, shows when it was recorded, the year, the day, month, hours, all of this. It includes location information, but your header data goes all the way through. It includes the location name, all the species are there, multiple species, and as I said, you very readily could have up to 5 species in this area in each individual file. That's perfectly fine. Spec is just who recorded it, and then your notes are there someplace in the world. That is imported into the Acoustic Data Management System, and I'll show you how that works in the next section. So, the mouse really has a brain of its own, it seems like. All right. That's one of the reasons we're using the analog. Not only is it free, but it's really quick and easy to manage large amounts of data from scanning through all your data really quickly in 15 minutes, 20 minutes, or whatever, scrolling by to identify what's in there. Also, if you've run auto ID programs on wave files, and it says there's 12 species in there, as you're manually going through it just very quickly, your eye will quickly pick up, oh, well, there's only 5 species in there representing 2 genera, 2 families, or whatever. So then you can start questioning it. Okay. So, data analysis and output. Once you've done 80% of the work or whatever, how you quickly summarize and analyze the data. The Acoustic Data Management System is used for managing everything. User-friendly R interfaces. R can be quite intimidating to a lot of people with all the command line things. Deducer is a real good free user interface if you need to do a lot of statistical things. Very user-friendly, great tutorials. I'm not the sharpest statistician in the box, so it helps me a lot. There are others, such as RStudio, that some people like. That can get a little more complex, but it's also really good. Excel or Notepad Plus allows you to edit header data really easily. You don't want to use word processing like Microsoft Word or any of the other open source word processors, because they embed all sorts of extraneous characters in your data file, your header file, when you save it. But you need to do that for some of that. R is very versatile, open source, free, large set of ecological data packages. Really great for analyzing your data after you have the output. Output results. One of the things you can do, and I do in R, is I do an overview of an entire data set, looking at just characteristic frequencies of all the data. Relative abundance summaries by locations and dates can be done through the ADMS. Relative abundance tables are exported, so you can do GIS density mapping. We use it for predicting characteristic frequencies for species we don't know yet. Provide temporal activity plots to see how the bats are sharing their space and time. There really isn't any niche overlap I found in a lot of the tropical stuff. They're just partitioning themselves in time, not in space. If you're just misnetting or trapping, you might go, oh, well, these two species are really similar. Different species, the same genus, almost the same size. They're probably feeding on something similar. How are they competing? Boy, this is real interesting ecological niche overlap. Turns out, in a lot of cases, they're not. The one guy's in there from 6:30 till 7:32, then they leave. And the next guy comes in. He's there till 9:20 in the evening. Then he leaves. And another species comes in. So they're sharing the habitat, but they're partitioning it in time. And using the temporal activity plots, you can really learn a lot on how the bats are using your habitat as well. And that's important if there's development nearby. Mining or other things, or wind generators. Some areas, wind generators are turned off during critical migration periods and not used, or during certain critical times of night. If your species that you're working on are really only foraging right after dusk for a couple of hours and then go hang up and roost for the night to digest, and are active again right before sunrise, well, maybe the ecological implication is for the consulting company or whoever, turn off whatever it is that's bad for the environment during these hours and go ahead and run it the rest of the time, and it may be all right. So you can learn a lot. Well, I'm hoping in continuing to freely distribute results. The fact sheets provide vocal signatures and other information on species distributions for all New World bats. I'm still searching for country collaborators for a lot of the South American countries. Also, there's interactive identification keys where you can look at your call frequencies on your screens and go through a whole series of interactive ID key functions. It's not really a dichotomous key that you're familiar with from an introductory botany course or plant tax or whatever. You have multiple choices. Like first, where were you recording the bat? That makes a big difference, because the moment you say, this county in Florida, that rules out a bunch of species that don't occur in this county in Florida. So you don't even have to look at those call parameters. And further down the line. Deducer, again, easy to use, can be freely downloaded from deducer.org. It's updated fairly regularly. I use it for calculating all the call parameter statistics, predicting call values. I save all the code in a simple Word document and paste it into the active R console as you need it. That way, once you have a working section of code to do your activity plots, for the temporal activity, extract call parameters, do all the basic statistics you need for whatever your data is. You can do it over and over and over, and you don't have to keep re-entering this stuff laboriously. You know, my whole thing is save time. You know, don't waste time doing things over and over. This is just a sample of a piece pasted out of one of my Word documents for extracting the call parameters. And the pound sign, you can't use it with your Anabat calls directly without removing it, because that's a comment signal for our code. But what I do is I just had a note for myself. This is the 6-digit species code. And if I'm going to run a new call parameter extraction and I have 50,000 calls that I want to extract the call variables and summarize the statistics, I just do a global search and replace in Word for those 6 letters with something new, and it does everything. It calculates everything, extracts things, writes the output file right where I want it, and there it is. There's a comma delimited file to open in Excel, ready to go. And I don't have to mess with the code ever again. It's right there. This also, I have one that actually includes all the harmonics and the fundamental frequencies, H2, H3, so it gives you a complete outline. But real easy to do. Menu driven. The plotting function is really good. Data visualization package for programming. Hadley Wickham, the New Zealander, who was at Waco, Texas, at the university. Now he's working with RStudio, and he continues to update all sorts of R programming packages. Excel and EndNote, or Excel and Notepad rather. Before you do any R programming, you need to just edit, do a global search for that character, and just strip it out of the file name, and then just save your data as text format, and you can do everything. How did the ADMS system evolve? Well, again, I needed to get to avoid getting sucked down the data vortex and needing quick answers. You know, any place I worked, I had a lot of data. You know, 60, 72,000 files maybe, depending on where I was, 1 to 5 species per file. I needed a way to manage the data. What it does, we've seen multiple species in the header data, and in each individual call file. What do? Each one of those species is a separate data record. Say no more, as Monty Python groups would say. It does it for you. When you import it, the moment you import it into the Acoustic data management system, it parses out each individual species and puts it as a separate data record in the master data tables. So if you have one call file and you have 5 species in it, the moment that's imported, that becomes 5 distinct unique data records as tidy data. So now when you analyze it and you ask for reports, each one is a separate record. You know, sitting with full spectrum programs, manually writing stuff down, looking at the screen with multiple species, that's ponderous. But you know, this does it in a heartbeat. Again, 80 to 90% of your work is the earlier demonstration. This stuff, you know, we were talking at lunch, Farah and her major professor, about her data from Peru, and she has hundreds of thousands of call files from different locations. You know, it may take maybe 4 months or so of work doing the 80% stuff. How long is it going to take to analyze it or to summarize it? Depends. Maybe a day. maybe a couple hours. I mean, it happens really quick. And it's all the automated repetitive stuff, but it also has 3 separate tables that are the key. The header data table has all the information that's been added to the species file, who recorded it, where it was recorded. Then there's a separate location table, which includes all the unique location names. It includes the XY GPS coordinates or geographic coordinates. And if you don't have a GPS, where you're recording, now Google Earth is free, their pro version. You can go in and extract a pretty good estimate of where you were and derive coordinates to add in here. It automatically calculates the acoustic activity index. This is what calculates the relative activity, relative abundance of each species, and separates that into a separate table so you compare relative abundance both by dates or locations or however you want to do it. This automatically, while you're importing it, it adjusts all your survey time or the activity index by your survey time. If you sampled one night at location B and you recorded there for 4 hours, but over here you recorded 9 hours, well, you've got different unit effort. You can't directly compare them. So you have to standardize how much recording was done by hour. So it automatically will adjust survey time based on the first bat recorded and the last bat recorded, assuming you don't have good field notes of when you started your work, when you stopped your work. Because you may turn on the recorder, it may go on at 6:18 at night and sunsets at 6:23, and in the tropics, the little sackwing bats are flying at dusk. They're already out there. But you may be in an open area that there are no bats out there till 7:02 at night, but you started recording, your data session actually was at 6:18. So you can manually put in what your actual survey time was if you want to narrow it down. It doesn't make that much difference, but if you want to be really technically accurate, there's a way to do that. But it automatically does that, and then it automatically standardizes all your activity index information by 10 survey hours. So you can compare between seasons, locations, species, times, dates, whatever you want to do. And that happens within the first seconds that it begins to get imported into the data management system. What it happens with a button push, and I'll show you the user selection in the system. You get the relative abundance by dates, locations, species. It's all user selected. If you only want to look at a single species, it'll give you that. If you want to look at everything from all your survey nights, survey locations, it'll give you that. It puts it out in a spreadsheet table format with 3 tabs. It gives you standardized acoustic activity index values, which is relative abundance, that you can actually use in the GIS and map, and I'll show you examples of that. It'll provide the temporal activity. It goes through all your data and sorts out each individual data record by minute for all of your data, by species, by each location, and then you can plot by each minute all the activity by each species. It also provides species lists for any New World country by administrative area. Some countries use states, like Brazil, some use districts, some use provinces, some use departments. The master database table for distribution information was extracted by GIS by taking all of the known species distributions, the big polygons, and extracting all the information. For the US, this is by every US state and county. We have distribution information now. that's based on what's updated. Some of it is based on the original polygons that IUCN and the Global Mammal Program did with expert input by mammalogists from around the world and various specialty areas. But all of that is in there. So if somebody came to me and says, oh, I'm going to Nicaragua next week, I've got a grant to record for 3 weeks, where are you going to be in Nicaragua? Oh, all over the country. Okay, well, I can send you a list of every species that occurs in the country with the subset of each administrative area, each district or administrative province, so you'll know what your suite of species are to even begin looking for before you start working through the identification. No point spending time trying to identify things that aren't there. Taxonomic changes, really? Well, what is it really? Well, we've recorded this bat and we're not sure what it is. Well, for some species, as going from Mexico to Bolivia and Cuba and in the US, species we thought we knew pretty well when we recorded them in Nicaragua, El Salvador, Guatemala, other places. Wow, the calls don't quite look like what we have in southern Mexico. Northern Guatemala is different than southern Guatemala where we've had them. Oh, the ones from Panama don't look at all like it. But when they key them out, oh, they look like they're the same. Well, the new DNA stuff that's going around lately with all the taxonomic stuff, a lot of these now have been identified as, really unique species, masquerading under one species. A lot of the old-time naturalists were actually true, the splitters versus the lumpers that describe new species or subspecies that since got lumped in. Acoustically, they're all different. And now it's making sense that, well, we weren't confused by the molossus from northern Central America. It's really a different species from what we had in El Salvador and Panama and other areas. So how do you deal with that with the database? Right now, the Acoustic Data Management System has 1.8 million call file records. So I've got a lot of data that's been recorded from all over North America, Central and South America, and the Caribbean. So when we start extracting call parameters, a lot of those are still unknown species. They're sono species. Unknown Vespertilion 38 kilohertz from Panama or whatever. But when we finally match a face to a voice, we can go back in now and in the database, and I can extract all of those calls. What happens is, the way the ADMS is, all the actual call files are in a big archived hard drive. It will actually go into the hard drive, copy each and every call file with that species in it, the 48 kilohertz or whatever it is, copy them over to a new subdirectory by country, and then subdivided by the administrative district, whatever it is, and then move all those call files over there. Then I can go in with Analook and actually look at those call files and go, oh, now we know what that is. Add the ID, remove whatever the unknown was, hit the button, it all gets re-put into the database, and then we update the global distributions of what we know is there. And so that was one of the things that was added a couple years ago with all the taxonomic changes. So I needed some way to manage huge amounts of call data. What's the AI or the Acoustic Activity Index? Eons ago, I was trying to figure out how to quantify bad activity. In the early days, there were a lot of past approaches. A lot of people were just measuring size of the acoustic data file, how many kilobytes it was. Well, that didn't tell you much because you could have had insect noise, wind noise. It wasn't all bat data. Bat passes has been used a lot in the literature, but that's kind of a nebulous, squishy sort of term. and it's almost uniquely defined by each researcher for what they meant as a bat pass. You know, one bat passed by and I've got a recording, or was it one bat flying circles around the detector 15 times? So bat pass didn't mean a whole lot to me when I was trying to figure things out. So back in the late 90s, I figured out a way to do this, and it was one of my earlier acoustic publications, but we came up with a whole method of determining the relative abundance of bats. And this is an effective measure that allows you to compare between sites, species, times, whatever. Essentially, it's simplified into the occurrence of the bat in your recording space during each 1 minute time block. So if this is my detector, and I've got one bat, and he flies around here for 3 minutes, 56 times, it doesn't matter. What it tallies is he was there 3 minutes, so he gets tallied as 3. It doesn't matter if there's 1 or 100 calls during that 1 minute time block. What I wound up doing, and this was off the corner of our office up on stilts in our house in Belize, and we had a bat feeder up, which essentially was a blacklight funnel trap without the insect catching device under it. So all the moths and stuff would come in to the blacklight, drop through, and the bats thought it was like, you know, Publix on a good day. They're just running around underneath, scarfing up everything they could eat. So I always had a big sample of bats of multiple species, families, genera, right by the house there, by the office. So what I wound up doing is capturing every bat while I was recording, removing them from there, putting them in their little cloth baggies, putting them inside the building where I couldn't record them, and continued recording till there were no bats left flying. And I don't know, I had 26, 28 bats or whatever it was. And then started releasing them again, one at a time, and they'd take off. Some just continued foraging, others went, oh, I don't like this, and they were out of here. But it actually turned out that it really worked out really well. It correlates with some of the other indexes, but it's unbiased. So it doesn't matter if you have one bat flying around your microphone a dozen times or 100 times or whatever, but it really gives you a good measure of abundance. It's relative activity, but relative activity really translates to abundance when you're recording. So that's all built into this, and it does it for you. Other than the Florida version, beta version that I released at an acoustic workshop I did down in Punta Gorda in 2014, it hasn't been released to other than a couple of people. The plan is to release it freely in the future, a working copy, so people can analyze, import their own header data and generate their own data reports and everything. User manual needs to be completed so people can figure out how to use it. It's Microsoft Access based, but it's embedded in it is a huge amount of programming code. It's not just a straight database. I investigated what Access or Microsoft calls a runtime version. That's available, and you can distribute it to anybody that doesn't have Microsoft Office with Access. And the basic Office apparently doesn't have Access. You need Office Professional or one of the other ones to get Access or buy it separately. Turns out the runtime version that you could use for free, you could go through the data and look at it, but you can't edit tables or add your own new data. The key is for the manual time. I'm busy doing a lot of things. I'd like to release this so people can use it. In some of the long-term workshops, that are 4 or 5 days, we actually go through how to use it. But to just hand everybody in here a working copy of it without a user manual, I'd be getting a lot of emails on a regular basis what do I do now? Funding, I don't know, maybe through the university we can find somebody to actually do the user manual in conjunction with me, and they'll be funded to do it. Almost more importantly, translated to Spanish, so it can be applicable to New World tropics. Spent almost $35K developing the program over about a 15-year period, and it's still evolving. Anyway, some of the examples of analysis. As I said, one of the first things I often do in a new area is look at a characteristic frequency density plot. What this does is take all the vocal signatures in your data and it plots the frequency density from whatever you set as a cutoff point, and automatically, without having any species identification information, you've got a species or a group of species in this frequency range. Another one here. There's something in here at a lower frequency range, but not as many as here. Wow. Over here, whatever that species is, likely a Vespertilionic because they're high frequency, broad bandwidth. So when you start going through your data to analyze it, before you've used filters or anything else, you automatically look, wow, there's 5 major groups of data that I've got there, or at least groupings of data. Some of those may be multiple species where the characteristic frequencies overlap, but it's a real quick way to look at what your data is before you even sit down to do other things. It'll help you start figuring out which filters you might want to look at first. Maybe you want to look for low-hanging fruit, look at the highest frequency stuff on the far right, and look for your species that might be in that frequency range. Filter those out, get rid of those, or maybe you want to get rid of the biggest chunk of calls and tackle the ones that are up around 60, 65. So that's one way to do it. Predicting plot of what the call frequencies are. This is really good. I put this together. This is for some of Farah's early recording data. These are the species of myotis that are known to occur in Peru. And what this simply is on the bottom, you see the species, and on the left is your characteristic frequency. Well, all this is a simple GG plot from Deducer. Just a couple of button clicks, you know, bing, 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 and boom, you've got a beautiful plot. You can save it as GIF, TIFF, JPEG, PNG, whatever you want to do for reports or publications. But the thing is, these 2 species, we don't know what they are acoustically. They're unknown species at this point. They haven't been verified, 2 species of myotis. Well, we ran the predictive statistics, the linear regressions, and this is where it's predicting the characteristic frequency likely is for those 2 species. So as Farah goes through her data, and I chime in from time to time to help tweak some of the stuff, we may have some myotis with some species overlap, but again, a lot will depend on her capture data. If she's capturing one of these unknown species, or has, hey, we may have matched a new face to a voice. But these plots are very useful, again, for big data management. Here's another one for an emballoneurid group, the Paroptrix species. This is showing both the characteristic frequency, the minimum and maximum, based on forearm size. As I said, the bigger the bat, the lower the frequency, the smaller the bat, the higher the frequency in general. So you start looking at the forearms, or the frequencies across the bottom and forearms on the left with the min-max FC. It gives you an idea of what the ranges are. Some of these sort of things are going to be included in the fact sheets as well, which I'll show you next. Overall, temporal activity, I talked about this. This is the time, wow, maybe I can't focus this way, but this is 5 o'clock at night going all the way till 6 in the morning. These are different dates, and at the top is actually the species. I'll zoom in for a comparison of two conspecifics in the same genus, Paralysis capilleri and Paralysis macrotis. The colors are actually different locations, and this is using what ggplot calls jitter. Instead of plotting everything in one line where they may overlap the dots, it spreads them out a little bit. So you can actually see a little bit better. You can plot them all in one neat little line, but having them spread out gives you a little bit more information. But you look at this species, at this location, it wasn't active till after midnight, and then just a little bit until sunrise. The next night, a little bit. But the other species in the same genus, it was active earlier in the evening, real active at the one location, after midnight. So it gives you a way to determine how the bats are moving around in time and how they're using the habitat. Again, the data for this is spit out of the acoustic data management system that you can just pull into R and then plot. I don't have GIS capabilities on this little notebook tablet, but this is an example from very recent Cuban data from December using GIS density plots, essentially where your size of your symbol is based on the acoustic activity index. The higher the index, the denser they are, the bigger the symbol. And I was able to do this with Farah's help. She created the shapefile in ArcMap, and then I was able to fiddle around in Google Earth. But you can see the bigger the circle, the denser the species was for the Cuban evening bat. Up there on the end of that little peninsula, they were really dense. And of course, in the GIS, you can do the symbols better where they're transparent and not opaque, and you can see how things overlap. But this gives you some information really quickly on how species are using habitat. Again, the data is tidy, comes out of the acoustic data management system. Pull it into a GIS as a text file. Real easy to create your shapefile that way, just a couple button pushes, and you're off to the races, as they say. Really impressive if you're a consultant and you're doing something for a client, and you say, well, here's what all the data is doing, or you're trying to impress your professor with your field work. You've got a lot of good ways to analyze your data. And the analytical part is really quick compared to the first part. Again, all of these things are essentially button pushes for you. Another PhD comics, and I'm hoping in the future you will only have grammar issues with your data. Okay. Few quick demos. In case you need to contact me, this is the best email for the Neotropical Bat Risk Assessment Program. As I mentioned at the beginning, I'm escaping Michigan winter. Having lived in the tropics for more than a quarter of a century, I'm not cold hardy. In Belize, anything below 70 degrees meant a second blanket on the bed. In this wind chill of -14 back home in Michigan, doesn't cut it. We were freezing up in Georgia where we were for 2 months when it got into the 20s at night. And that was not fun. But I won't be back in Michigan until April. I do have email while I'm on the road, and I can certainly entertain questions and answer people. I can assist with data IDs. If you've got a data program, in your case, if you've manually vetted some things, you wanted a second opinion, feel free to send some of the ZC extracted files or even a couple of the WAV files. It's a little more difficult because we've got a Verizon hotspot for internet, and WAV files suck up a lot of bandwidth. So ZC files are easy to just zip together, and email is a little attachment. They're tiny. Okay. I'm hoping I can get the mouse to work. It's been sluggish. Oh, I see. That's this other mouse. No wonder I'm confused. All right. First off, we will look at fact sheets that are put together. These are available in HTML format, so you can look at them in your browser. Also, they're written and output as PDFs, but the interactive feature of it is not working as a PDF. But when you open the fact sheet, this is one that was just very recently completed and distributed for Cuba, for the Canadian biologist and some Cuban biologists. I do have one for Florida only that was done in 2014. It needs to be updated a little bit. So if anybody's working only on Florida bats, I'll be happy to send that to you. Farah and I are working on the one for Peru. I've got Guatemala, Belize, of course, since that was my home stomping grounds for forever, and a number of other countries. But if there is any students or researchers from other Latin American countries that might be interested, I'd be happy to collaborate with them, and they can look at things. Well, the fact sheets, at first, we're in the index file. The very first of it, you just open it up where it says index HTML, and these can be zipped or compressed and emailed fairly readily, or put to a Dropbox for people to download. The index includes all the alternative names that were in Spanish for Cuba. Also includes synonyms. The broad-eared free-tailed bat, at one point it had all these other taxonomic synonyms, common names, all of that. Up at the top, you can just jump to the ends. Let me go back to the top for a second. Included in this and interlinked in each of the species accounts, which I'll show you, is a glossary. You go to the glossary, all the definitions, all the terms that are used are completely spelled out. Tells everybody that's using them exactly what it is. Kilohertz, actually named for Heinrich Rudolf Hertz, who was the first to prove the existence of electromagnetic waves. Bit of trivia, but that's all there. It just opens in whatever browser you're used to using. Let's go down to the Nictisius. Here it is. The Cuban evening bat. You open it up. It gives you taxonomic information, the family name, database species code, gives you the call shapes, shows you a description of the call shapes. These are broadband, Vespertilianid. Generally, an example of what the calls look like. These are compressed calls with all the empty space in between the pulses removed, so you can see the call shapes better. Keep going. All the vocal signature parameters that we've talked about are in here for each species. So you've got the, oh, that's interesting. This didn't display correctly with the header. There's still a glitch in the software. The software that helps me create these is based out of Australia. And I sent an email to him yesterday, but because we're on a not quite 24-hour time zone difference, he didn't respond. But source of data is included on who provided the data for each call sequence. All the IUCN conservation status is included in the acoustic data management system. That's always updated. So as you start extracting data from the data management system, all the taxonomies in there, species distribution globally, IUCN status, all of those are part and parcel of the relational database that's already built in there. And then there's citations for anything that might be useful for people. And Anthrozoas, that's another species from Colombia, or found on Cuba. This is a real broadband bat. You look at the, but each of these call sheets, you just look at them in your browser. Well, this is really disconcerting that didn't display right. But yeah, you've seen the examples before. It shows you the, with N and everything. Somehow it's moved everything way over there. But the distributions, it shows the known distribution in Cuba, what the subdivisions are, the administrative districts. In this case, this species has been found in every area of Cuba. Under notes, no recordings from Cuba at this point. And then you can simply go back, or you can go to the index at the top. Look at Aptesicus, big brown bat. Again, it's found everywhere. There's almost everything in Cuba is found almost everywhere on the island because it's an island. Some of the species, oh, this was a new one. The Cuban biologist that was there. This shows characteristic calls for the genus Laziurus. The species move up and down. It's different than other Vespertilianids. That's really characteristic of the genus. Doesn't matter what species or where in the world you are. If you've got that genus, as I said, the characteristics are distinct. But we now have call parameters and everything thanks to her work of 9 days in Cuba last December. So we've got over 4,000 call pulses that have now given us this. This was a species that was previously unknown acoustically. So there's only a couple places in the Caribbean that could be. So that's how the fact sheets work. Oh, go back in. Talked about the glossary. If you highlight the terms and you go over to it, it actually pops up the glossary terms and explains what each thing is. So that's in the glossary as well. So if you're new to bat acoustics, hopefully freely making these available to everybody is going to help you identify your species a whole lot quicker. We'll go quickly. What are we doing on time? Ooh. Okay. We're going to be close on time, but we're going to do all right. This is the acoustic data management system. This all kinds of tables that I've spit out for people. Somebody needed data for Ecuador. And this was showing all the species that occur in Ecuador with their code, the country code for the database, and then the administrative name wherever they are. There's he was working in 2 different districts, so I sent that to him. So those are readily exported and will be in the main version. But what we need to do is go to the forms. Import header file. It's a nice little simple thing. You saw me export the header file and save it for the ID added. So we're going to go to that one. And there's the header data. And it's a slow computer, but you can see it going through the processing there. Okay, what this does now, this renames the header file to done. So when you look at your data, you know you've already processed it. Now it's calculating all the survey time automatically for you. And again, this little laptop, it's more of a tablet than a computer, goes really slow. I'm sorry. This would have been done, you know, in a heartbeat on a real computer. It's calculating the acoustic index and standardizing everything. And now it's ready. We're all done. Now we want to look at this. We can now go and export the data. Let's remove all. And remove all. So what we can do is you can go to the country code and look up whatever country it is you're working in. So if we do Cuba, add all locations for Cuba, all the locations are there that there's data from Cuba now. What family? You only want to look at one family's worth of data. It's user selected, but we only want to look at one. Let's look at the mustache bats. What do we want to look at? Let's look at this one. Add species. So this will give you a deal there. Start date, well, depends on when you were surveying. Add all dates. Going slower. Again, with a real computer, I think like I said, your processing power on this. Now we can actually write it somewhere. You can browse to where you want to write it. Or you can actually save it by location, and unfortunately, it's not a good example with a tablet. So I can just look at it here without writing it out. But this is showing at these locations, there's the coordinates, here's the dates, here's the calculated survey time for each one of these in hours. Actual survey time was entered. AI values for this single species. Here it is standardized or calculated according to your survey time per hour. And it'll also give you start and end time of your survey. So all your summary data is already completed. I mean, it's literally a button push and it's all there. If you needed GIS data, you can actually look at it as GIS data. Use your species name, the dates, location names. There's, your geographic coordinates, altitude if it was entered, if not, AI value. So you can immediately import this into your GIS and it'll give you your density plots. All you need to do is just write this out. And even though this was a bit slow here we've looked at, data really quickly. So the analytical part is really, really quick. This just makes all the tedium of the analytical stuff go by really quickly. So that kind of in a nutshell is there. All these tables are interrelated. Bat sizes are in there, call shapes, call types. The taxonomy, the bat names table includes Spanish names. We need a lot more Spanish names. Portuguese names are probably going to need to be added for Brazil. All the taxonomic information is there, genus, species, author. And more importantly, as you export these, it keeps track of, do we have calls? Is it a known species? Or do we still need calls for that species? What's the call shape? Frequency modulated narrowband. U-shaped calls, and all of this is in there. Fact sheets. Do we already have fact sheets for these species? Source reference. There's literature references for new taxonomic updates. So all of that is interrelated. So we know if the species we're dealing with, we have calls that are verified or no calls exist, and we can go from there. So those are ways I developed to manage data, because it's a real pain to reinvent the wheel every time you need to do something. And hopefully the tools will make everybody else's work a whole lot easier. And going through the iterations in Analytics takes time, but it's certainly a lot quicker than manually looking at a screen of ink blots with full spectrum stuff, which is really hard, especially if you have multiple species in the same file. It's real hard to tease out with full spectrum stuff. This will separate out. Learn how to use the filters. You can build your own. There's a whole base of filters for all the known species already that are going to be available to everybody. So anyway, that's why there's big data concerns with bats. It's not a real simple thing on one hand to identify the bats, but it doesn't have to be paralyzing on the other. If you don't know what it is, can't tell, sono species. You can tell a vespertilianid from a molossid by call shape, for the most part, if you're looking at search phase. Commute calls can get a little complex, but again, with little experience, you won't have any problem with it. So, thank you. If there's any questions, I'd be happy to go. Somebody in the back.
So a lot of these specialized software where you go through the menu, I mean, it's designed for a very specific purpose, and you go through the menus, but the menus show you where you can go. Can you like click on things to get the code out of it? Like, could you use some kind of code interface? And then the other thing is, if you can use that code interface, then you can document all your changes and have a record of like everything you've done.
Yeah, the programmer I'm working with for the last 10 years on this, for 12 years, that's all documented. It's all Microsoft, not Basic, I'm trying to remember what it is, but it's embedded within the Access program, and all the code is there. None of it's locked. I mean, it's accessible. But there isn't a code interface, because they're all linked to multiple interrelated tables that are all relationally linked. So if you use a species code, either a 4+4 for US or a 3+3 for other New World areas, that's automatically linked to the taxonomic table. And all you need to do in your back call files is just use the little short things, because it's ponderous using species names or whatever. And it's also much easier to update. But everything is interlinked inside. And it's real easy to, if you're familiar with Access, to add your own queries and generate other ways of looking at the data other than these standard reports that are used over and over and over to generate relative abundance, density, temporal activity plots, and everything else. So those are the most common features that are used. And then from there, you know, in your R and other statistical programming and ecological programs, you can determine, you know, well, what do these numbers mean for site A to site B? And this one just got pesticided by a crop dusting plane, and this one didn't. How do I test that treatment plot or whatever? Then you use the data that's already there, you know. Anyway. Yep.
Do adolescent bats do they call it a higher frequency than a fully grown bat, or is there not a lot of variation in their calls?
Once they're free flying and out on their own, it's pretty much the same. In the roost, they're really audible squeaking, almost like little mice or something. If you go into a roost, or if you have them in hand, they scream and holler in human audible tones. I mean, and it's, if you're misnetting in the tropics, it's like you wish you could stuff a rag in their mouth, you know, because you get a big fruit bat, and he starts, all of a sudden 50 fruit bats start hitting the net all around you, mobbing you, and suddenly you've got your hands full trying to get all these bats out, you know, unharmed, and they're chewing holes through the nets that Land Rovers could drive through. So when they get these audible distress calls, you know, and some of the big fruit bats in the tropics literally will, you know, crunch the end of your thumb. Their bite strength is really, really hard to go through the real tough fruits. Unlike the insectivores, which are all sweet and docile little things, except for the big beetle crunching mollusses. Okay, well, thank you everybody for coming. And if you think you want copies of stuff, I guess you can contact Farah or email me. You know, as fact sheets are available for various areas, or we get ready to, if you need a specific set of tools or a copy of the ADMS for a specific area, a lot of the extraneous stuff can be stripped out. The Florida only version was really good because the taxonomy table was real small. It just included the Southeast US bats, a couple species that may or may not occur in the Panhandle were included, and stuff like that. But all the tools or the mechanism that simplifies everything and parses everything out and calculates everything just like that, that's all in there. So your own data goes in, boom, it's done. You extract your relative abundance tables by dates, locations, species, however you want to do it. It's user-driven menu, or you can just say, give me everything, the whole enchilada, and it'll, or the full Monty for those that saw that film way back when. But anyway, there it is. Hopefully it'll contribute to other people's work.
Thank you very much.
Thank you.